So we've got two competing camps in the field of people who say, no, there's nothing to worry about, it's going to be fine. And then the other side saying, actually, it's going to be a big one. So we've got 5 years to like make sure we're okay. So we know there's an active season and a less active season. So right now, at the moment, we're in a less active season, we're at solar minimum, but we're just seeing the start of the next solar cycle. So we know that in about 3 or 4 years' time, there'll be an active period, very roughly. But we can't predict that. So if we understood better how the sun's magnetic field changes in time, we could predict the seasons. There's some people that say, oh, it'll be a very low, it won't be very active. There are other physicists who put together a fancy model of the sun, and even though last cycle was not very active, we're going to predict a really big one for next time. Yeah, so lectures are all online, so I record them a week or so in advance, and yeah, so I've got amateur YouTube setup. That's how I see it.
Like, as do I.
Yeah, you wouldn't.
As you can see everything behind me.
Yeah, you wouldn't want. I wouldn't be a very good YouTuber, but I've got all the stuff now, so maybe I should. I don't know.
Oh wow. Are you finding it really challenging with students, like with it all being all online?
It's definitely different. Recording videos instead of lectures is a completely different skill set, it turns out.
Right.
When you're lecturing, you prepare some material, you go in, but then it's like a free form, you perform in front of them. And so you write things on the board, you talk to them, you could look at them and you can say, oh, you're asleep, or you're excited, or you're confused, or so you get a feedback on what you're saying, and you can modify it as you're going through. A video is much more like a TV program. You need a script, and you need to stick to it, and you need to present your material as clearly as you can, and there's no feedback. So I think the average lecturer who's used to preparing some notes and then using their own knowledge to kind of flesh it out in the classroom and just discuss it, that's very different to doing a video. What you really want as a physicist or a mathematician is a whiteboard and a pen and to do some maths.
Do you think anything will sort of stick around after we're back to doing everything in person? Especially I feel like universities are going to go, like the in-person benefits at university is so much higher than what a lot of people are talking about from working from home, right? So it seems like there's going to be more of a rush to get students back into classrooms. But do you think some stuff will stick around?
I don't know. Yeah, I hope so. I actually think the videos are good for certain topics, right? If you're doing a lecture which is just about conveying information. So if I'm teaching solar physics, there's really nice videos of the sun taken by telescopes in space, and you can see the solar flares and sunspots and stuff. That stuff's all great via video, because I can narrate a video of all these different images, and that's great. There's no I can save that, and then I've done it once and I never have to do it again, and the students can watch it as many times as they want, and I can use that every year going forwards. I think that one of the hardest things students are finding is the lack of interaction, right? I speak to my tutees and the people in my project students and stuff, and it's like it's very frustrating for them. I just sat in their bedrooms watching videos and it's very isolating, and I don't think they feel like they're I've actually had two students say they missed the library, which I didn't think was going to be such a big thing, but I do understand, that they had a separate space from their bedroom that was quiet and had the atmosphere of I'm studying, I'm learning, and they don't have that anymore. And now they're forced to, sit on their bed or sit at a small desk in their little student room and halls, and you just think, yeah, I get that. I don't think that's a very good way to study.
You're at risk of being interrupted by beer at any point.
Yeah, and you have noisy neighbors and stuff, right? The person living above you or to your left or right might not know that you're working then, or may not care, and maybe playing their guitar or or whatever else. So
And a really big part of going to uni for like new students this year is networking, right? Is meeting other people who are going to be your colleagues in the future, or just making friends if you're at an undergrad. Like, I can't imagine how. I think if I was going this year, I may have just deferred. Has that been a problem?
Um, I wasn't that involved in admissions. All I know is the sort of headline figures, which is, we admitted slightly more students this year than last year, but not fantastically more. So it doesn't seem to have had a negative effect in terms of raw numbers. But whether that's because a whole bunch of people deferred to next year, and then a whole other bunch of people got their grades that they didn't think they were going to get, and so have decided to take advantage of that and just go for it. I don't know.
Yeah, yeah.
But
Wow.
we haven't seen a massive change in numbers. I know other universities have. So I know the Russell Group, like the Oxbridge and Imperial and UCL and all that. I think they've seen a big boost of numbers. So it must have affected. It's gone the other way, right? People haven't said, "Oh, I'll stay away." They've said, "Oh, I can't get a job." Or, I mean, what's the point of
Right.
having a gap year if you're going to spend it sat in your bedroom in your mum's house?
Yep.
I may
Yep.
as
Very
well.
true.
I may as well go. Can't earn money, so I may as well go to university virtually and get a year ahead in terms of getting a job eventually. So
Yeah. Yeah. Everybody's doing everything virtually, so I may as well
yeah.
start studying. Yeah, that's so true. Well, I haven't even said thank you. Thank you so much,
Ah,
Rob, for coming on. Like, usually that was really interesting. Usually, we're talking about people's research as well as sort of their teaching. So, how has COVID sort of affected your research? Because I suppose with studying space and our local solar system, your probes and satellites that you feed the data off, they're already out there, right? And they're not going to get coronavirus.
yeah. So I mean, in terms of the stuff that I do day to day, it's almost, I wouldn't say beneficial, but it's almost beneficial in that I'm working from home, everything's virtual. And when I was in my office, people come and bother you. They knock on the door and say, "Oh, can I just ask you this question?" That doesn't happen anymore. So if I just turn off my email and say I'm busy, then I can sit here and do my research and get a lot done. So it's been quite productive. And yeah, you're right that the satellites and spacecraft are already up there. So that there have been some bumps for the projects that are not finished. So, you know, um, uh, I work on a few future missions as well, and the labs where they're being constructed or tested are had to close for some period of time, and so there's been delays to a lot of projects, and delays will mean budget overruns because they're still paying the engineers and they're still buying the parts. So you know, well, I guess we don't know how it's going to play out yet, but the budget for the space agency for next year might have to be a bit different than it was going to be. But that's up to the government to figure out, right?
Yeah, yeah. What
So
where the priorities are, yeah.
yeah, and these are ongoing projects that are international that we're committed to, and um, if we back out of them, then uh, that's at our own reputational risk, right? It's probably to our benefit just to pay our share, right? We're not going to pay everything because it's an international project, but whatever the cost overrun is, we should pay our share of, because that's how you do big international projects.
Yeah,
Um,
yeah. That's how we do space stuff as humans, right?
yeah, well, I mean, that's exactly right. So even NASA, the richest space agency in the world, still collaborates with other countries to get some missions done because they're just so difficult and so expensive. So it's definitely never, almost never, one person or one country doing something, right? It's a big
Right.
international collaboration.
Is that
Um,
something that we kind of left behind in the space race age?
um,
Or even then, were people sort of collaborating anyway?
no, you are right. It's something that's happened over time. So you know, to begin with, I guess in the 50s and 60s, everything was a national priority, right? So America was inventing rockets, and NASA was about to start, and so that was very militaristic, and it was focused on USSR and the Cold War and the space race. And the UK had a role in that we don't publicize very well. The UK had its own rocket that was launched, and launched several things into space. There were satellites launched from the UK into space back, or at least from British controlled territories.
Mm.
And so the UK is the only nation in the world to have had the capability to launch things into space independently that has given it up. So, you know, our Skylark rocket was a British invention that launched satellites into space, and then we stopped building them and just gave up doing it. And now, I mean, for a reason,
Right.
in that the European Space Agency was becoming a thing, and so the UK government said, well, great, we'll pay our fees, our dues to the European Space Agency, and they'll launch rockets for us. So
Okay. So was
I
that
think that's
during
fine. But
the sort of formation of the EU and the sort of
yes, that
coming
was like,
together of those
yeah,
powers?
that was the 70s and 80s kind of period, and then in the 90s, the European Space Agency became a more coherent thing, and since, you know, the mid 90s onwards, the European Space Agency's been a you know, first-rate international space agency that, you know,
Yeah,
builds massive
absolutely.
rockets, the Ariane 5 and so on, you know, and
So, uh,
launches separate
yeah,
missions.
yeah, yeah. Are the UK going to pull out of it in Brexit? Is that part of the Brexit negotiations?
Thankfully not. So the European Space Agency, although it's got European in the title, has nothing to do with the EU. It's just a
Hmm.
separate body. In fact, there are, you know, Canada is an associate member of the European Space Agency. So it's a bit
Okay.
like Eurovision. You don't really have to be in Europe to be a member. As long as you
Okay.
pay and turn up, then you can join in. Um,
That's
so
cool.
yeah. So
That's
yeah, if you ever watch European Space Agency presentations or go on the website, there's all the little flags at the bottom, and you know, you recognise most of them as European countries, and then some other ones pop up, and you're like, I didn't know Canada was one of those. But yeah, there you go.
That's
Um,
cool. Okay, that's nice. And these are what your missions that you're working on are there with the European Space Agency.
yes, yes. So my big mission at the moment is Solar Orbiter. So I don't know how much you know about that, but it's a medium size European Space Agency mission. So everything in space is, the names are weird, right? Medium, what does that mean? Well, it's still really expensive, right? It's like half a billion, sorry, euros. So it's a big mission.
Mm.
It was launched at the start of this year, and its mission is to go and look at the sun. And so it's going inside the orbit of Mercury eventually, and it's got cameras on board to take photos of the sun in various different ways to look at how the sun evolves over time, and it's going to tilt its orbit out of the plane. So if you imagine the sun and all the planets in a disk, like in a plane, the
Hmm.
solar orbiter is going to go out of that plane and orbit like this, so that it can see the north and the south pole of the sun. So we'll get the first ever photographs of the north and south pole of the sun from solar orbiter.
I didn't realize the sun had poles. So, because,
Yeah.
okay, so that's to do with its magnets, right? It's magnetic.
Well, so there's two kinds of pole, right? There's the fact that the sun and planets are all spheres that rotate. So you have a pole in the sense that the sun is rotating round about an axis,
Hmm.
and then yes, it has a magnetic field as well. And the magnetic field of the sun is a big mystery that's actually very important. So um, a bit like the Earth, it has a magnetic field that's a bit like a bar magnet, right? It goes out of the North Pole, around and in back through the South Pole, so making these kind of loops like this.
Mm.
But the sun's magnetic field flips over every 11 years, roughly, in the solar cycle. So sunspots appear on the surface of the sun, which are these dark patches that are made of very, very intense magnetic field. And over 5 years, they appear at the equator, drift towards the poles, or sorry, drift, so appear in the middle and drift towards the equator, and other bits drift towards the poles. And through that process of moving the magnetic field around, the entire magnetic field flips over. And so we can observe that on the surface, but we don't really know exactly how that happens. So
Mm.
it's a really massive part of the sun that we don't understand, and it's very important because sunspots are the places where solar flares happen most of the time, and where coronal mass ejections happen. So these massive explosions that shoot off tons of gas out into the solar system, and that's what causes us space weather. So
Hmm.
it's seeing the north and south pole of the sun will help us understand the magnetic field of the sun, which will help us understand space weather, which might help us, protect ourselves against the radiation and geomagnetic storms and other things that happen because of space weather. So it's a
Okay.
long process. Don't expect results tomorrow, right? There's a science mission, so in 5 or 10 years' time there'll be some exciting papers about about these
Yeah,
things. But
yeah, yeah.
that's the end. That's one of the end goals of the mission. So
Oh, Right. So when we talk about space weather, we're talking about what's going on in the sun and how it affects sort of like the solar system around it, right? And these sunspots and coronal mass ejections, they're the events that happen.
Mhm.
And so, right, so by this work that you're doing is trying to sort of understand the patterns and better predict when these events might happen.
Yeah, so I mean, weather on the Earth, we have a weather forecasting service, right? That we
Mm.
want to know whether we need a coat tomorrow or an umbrella, or maybe we just stay at home because it's so awful. Or if it's going to be sunny, we'll all go to the beach, right? So it's that that's the we want the same thing for space. So the weather that we experience here is predictable in the sense that we understand a bit about how the air moves around and how
Mm-hmm.
we can model that. And then if we take some observations, we can put the observations of the model together and try to predict the future.
Mm-hmm.
The same thing we want to do for space weather, right? In the space, weather is the winds that blow against the Earth and the radiation that comes with them sometimes. Because that wind from the sun, the solar wind, is coming along and it's pushing against the Earth's magnetic field. So if you have two magnets and you try and push them together, right, they repel each other.
Mm.
So something similar happens in space. The sun has a magnetic field that comes out in the solar wind, and the Earth has a magnetic field, and they push against each other. And it's not very strong, we don't experience that, but it's enough to deflect the solar wind around the Earth. So that our magnetic field protects us a bit from the solar wind,
Yeah.
but it also means we have geomagnetic storms. So that if the solar wind pressure, if that wind from the sun changes rapidly, it squashes the Earth's magnetic field. When you have a rapidly changing magnetic field, you get an electric current. So a geomagnetic storm is just a big electric current in space that makes an electric current here on the ground. And that electric current on the ground goes through the power grid because, before humans existed, it would have gone through the crust of the Earth and no one would have noticed.
Mm-hmm.
But we have covered the Earth in this nice long conducting metal wires. So the electric current prefers to travel through that. So it does. But the problem is we designed the system to carry the current that we made, not the current that's coming from space. So it
Yeah.
tends to trip the safety features on the electric grid and cause blackouts and things like that.
Mm-hmm.
Um,
And
so
that's why
yeah,
we want to know when is it going to happen.
right.
So in the same way you were saying about we know when it's going to be sunny and when it's going to be raining based on weather forecast,
Hmm.
but obviously also we have seasons. We know it's going to be colder in the
Hmm.
winter, depending on where you are in the planet. And so what you're studying will help us understand that magnetic shift, which is kind of like the sun's season.
That's exactly right. Yeah. So actually, both of them. So if we understood better how the sun's magnetic field changes in time, we could predict the seasons. So we know there's an active season and a less active season. So
Oh
right now,
wow.
at the moment, we're in a less active season. We're at solar minimum, but
Uh-huh.
we're just seeing the start of the next solar cycle. So we know that in about 3 or 4 years' time, there'll be an active period, very roughly. But we can't predict that. So throughout this year, there've been all the solar physicists have been making their predictions for the next 5 years. So if you go on
Yeah.
Twitter and follow some solar physicists, you can see they're all making their predictions. And there's some people that say, "Oh, it'll be a very low. It won't be very active. Last time
Mm-hmm.
wasn't very active, so next time won't be very active." That's the approach of like yesterday was sunny, so today will probably be sunny, right? There are
Okay.
other physicists who are using advanced data analysis techniques that say we've put together a fancy model of the sun, and even though last cycle was not very active, we're going to predict a really big one for next time. So we've got two competing camps in the field of people who
Mm.
say, no, there's nothing to worry about, it's going to be fine. And then the other side saying, actually, it's going to be a big one. So we've got 5 years to like make sure we're okay.
But that's like
And
saying, okay, well, yesterday it was sunny, today it's sunny, tomorrow it's going to be sunny. But also, oh, it's going to rain sometime. And usually when
yeah,
it's
right.
sunny
Well,
for a
so
long period of time,
yeah,
boom.
so exactly. But that's the thing, right? If you base your weather forecast on what the weather was like yesterday, you get it right a lot of the time. It's
Mm,
actually a pretty good forecast. The problem is it doesn't catch when you have a change, and when you have a
mm,
change is the thing you really want to know.
mm.
So, you know, who knows who'll be right? We have to wait 5 years and see. But
But
it's
we're
that's
quite,
that's
we're,
kind of where we are in terms of the long-term forecasting. But there's also
mhm,
short-term forecasting, right? So, we have a weather forecast that's accurate for like 2 or 3 days into the future, roughly, at the moment, for terrestrial weather.
mhm.
And we want the same thing for space weather. At the moment, we have the forecast for space weather, and I'm, apologies to the Met Office who do the forecast, but it really isn't that great. Like we can't forecast solar flares at all, really. We just say there is a chance of a solar flare happening based on the magnetic field we see in the sun, and it's a rough kind of percentage. And we don't really forecast coronal mass ejections before they happen. So the explosions that release this big bubble of gas out into space, we can't really predict them. Once they happen, we can track them coming towards the Earth and calculate the arrival time. And that takes, if it's a normal speed one, it takes about 3 days to get to the Earth. So you might get 2 days warning.
Okay.
But the problem is the normal speed ones, that's like just a normal storm, right? It's good to know, but it's not actually dangerous stuff.
Okay.
The really dangerous ones are the ones that go very quickly because they're very energetic. So, what's considered like the worst case scenario for a coronal mass ejection is one that would leave the sun and then arrive at the Earth in about 17 hours.
Oh,
So
right.
the problem is it takes 4 or 5 hours to process the data to tell that it's coming. So you actually only really get, maybe if you're lucky, 12 hours warning that this really massive thing is coming. So, and that's the problem, right? If you say to the national grid, you've got 12 hours, there's going to be a big geomagnetic storm, they say, oh, well, it's too late. We've already given all our engineers their schedule for tomorrow. We can't do anything. National Grid says we want 5 days warning of a coronal mass ejection so that we can do stuff, that's practical, right? That's their timescale for changing things to make them safe. So we need to have a forecast for CMEs that's 5 days into the future, and we're very far off that at the moment. So this is another goal of Solar Orbiter, right? Is to link together what's happening on the sun to what leaves the sun and comes and hits the Earth. And if we understand that better, we'll make better models, and then we'll make better forecasts. And maybe one day in 10 or 20 years' time, we'll have a 5-day forecast of space weather that means that we can adjust the national grid to be prepared. And I should put this in context of, it all sounds very dramatic. Oh, massive explosions and there might be a blackout and all this. But actually, we've lived without a space weather forecast, for forever until now. And, it's not like we're all experiencing awful outcomes because of space weather. The problem is the nature of how we use technology and how we use space is changing. And so we're becoming more and more dependent on it. So, in 1989, there was a huge space weather event that knocked out power in Canada, in Quebec, a region of Canada, for a while. And, that was a major thing at the time. But the satellites that were in space at the time were also affected. The thing is, in 1989, only people with a car sat phone cared, which is that it was them in the military, and that was it, and no one else knew, right?
Yeah.
But if that happened today, and you had a blackout of satellites for a couple of days, I think it would be an absolute disaster, right? No one knows how to read a map anymore. You just get your phone out, you put it on your car, and you say, "I'm going there." And if that didn't work for a couple of days, I think there would be an impact, right?
Yeah, that would be. I mean, I was going to ask, so obviously you were talking about the national grid, you're talking about the UK, and earlier we were talking about how a lot of things are more international. And I wanted to ask, is this awareness, is this like data processing to prepare for this kind of thing happening on a wider scale? But how come it just took out Quebec? How come it happens so locally?
So that's a geographic thing. So the currents that flow are stronger where the magnetic field is stronger. So the northern magnetic pole is actually just north of Canada. So Canada is one of the places that gets affected by space weather the most. So the closer you are to the northern magnetic pole, the worse the effects are on average. I mean, there's also some localization, right? So just like a big storm will have, like if it's a hurricane, you've got like the eye wall, which is where the most intense winds are, and so where that makes landfall is where the most damage is. Geomagnetic storms are similar in that they have what's called a substorm in them, which is where the most intense current flows, and that substorm is localized to maybe a few hundred to 1,000 kilometers somewhere in the world, and we can't forecast that either at the moment, right? It just is where it is.
Yeah.
So if we
Right.
had a better
Okay.
model, we could forecast that maybe. But so in 1989, that substorm was above Canada, and the reason Quebec blacked out again is a not an accident, but a an unexpected design fault, right? So they Quebec has a hydroelectric dam that provides most of its power,
Mm-hmm.
and that connects to a big long trunk line of electricity cables that runs north south through Quebec. And so what happened was the substorm was above one of these transformers in this power line, and it knocked it
Mm-hmm.
out. And then the safety systems kicked in, and the next transformer along said, "Oh, I've got too much current flowing through me. That's unsafe. I'm going to turn off." So it turned off,
Right.
and then the next one did, and then the next one did, and the next one did, and so the whole power line just unzipped, turning itself off. It took about 90
Right.
seconds from the first one turning off until only the transformer next to the hydroelectric dam was still running, and that one can't turn off because it's attached to a dam that has water flowing through it, and it's making electricity through water motions. You
Mm-hmm.
can't stop it, so the electricity
Mm-hmm.
has to go somewhere. It went through that transformer and just melted it.
Oh my
Transformer was
God.
completely destroyed, and that meant the dam was cut off from the power grid, so there was just no electricity.
Right. Okay. But it doesn't pose a danger to life or anything, right?
No, not directly. So I mean, if you're in
It's.
space, if you're an astronaut, there's radiation that is definitely a problem. But
Mm-hmm.
that's a very very small number of people, right? For most of us who are here on the ground, it's extremely unlikely that you would die from space weather or be injured, right? It's something
Mm-hmm.
that affects the power grid, satellites, and the radio basically.
Mm-hmm.
There's a very very small amount of evidence in sort of obscure Russian medical journals about studies to do with pacemakers, because if your heart is attached to an electronic device and the electric
Right.
field around you changes, you might experience something. And also actually to do with things like migraines and depression, because um, there's actually quite a strong electric field between your toes and your head. You know,
Mm-hmm.
it doesn't ever affect us, right? Because we're our biology is used to this; it exists. But the
Yeah, we
geomagnetic
live with it.
storm, yeah, the geomagnetic storm changes that electric field. So again, it's not clear that all
There
of
is
this is
some,
very
yeah,
fringe science, but
right.
there's some evidence of more reports of migraine, more reports of depression, and more reports of pacemaker problems during severe magnetic storms. There's
Right.
also reports of things like whale strandings and pigeons getting lost, and so
Oh, that makes sense.
animals that are sensitive to the magnetic field of the Earth get confused when there are
Mm.
geomagnetic storms. That's the theory. Now, I'm not a biologist, and I think the evidence is a bit. Um, we need to do more studies to be sure about that. But
Right.
but it's possible that it directly affects people.
Right.
Can it be linked to any deaths? No, I don't think so. Like, there's no real evidence of people dying because of space weather.
Yeah,
Um,
yeah. It's more the
but
indirect sort of, yeah, like you were
yeah,
saying, GPS not working. But so we're not going to be waking up in some sort of zombie apocalypse or anything like that. It
shouldn't.
happens in quite a small area, and we
Yeah,
have
so I mean
things
that.
in.
So the controversy there is, the storm that happened in 1989 that knocked out power in Quebec. It
Mm,
also has some effects in Sweden. So it is a global thing. It's just the strongest effects are in one place.
yeah.
Um,
Okay.
and there have been other storms since and before that we've also studied, but the biggest recorded storm was actually the first recorded space weather event, which is called the Carrington event from
Okay.
1859. So um, um, that event was actually the first observation of a solar flare, because Victorian scientists in London and Germany and other places around the world were looking at the sun through their telescopes, and they saw Richard Carrington, who was in London, saw this big flash of white light, um, and about a day later, the magnetic field of the Earth went crazy, which they were measuring in Greenwich, and they put it together that this flash of light on the sun had caused the change in the magnetic field of the Earth, and so that was the first
Oh,
um, true linking of the sun to the Earth in terms of geomagnetic storms.
right.
We now know that to see a white flash like that of light means it must have been a huge flare. So
And
this
one
is
hasn't happened like that for. almost
Well,
200 years.
this is where it gets difficult, right? You have to start doing statistics. And it's very difficult to know because the observations made by Carrington and his contemporaries, um,
They may have been
not
exaggerating, right? They may have been
well,
overexcited.
it's not the exaggeration so much. It's just that all they were doing was looking through a telescope with their eyes. These days we
Mm-hmm.
measure flares and we actually categorize them by the X-rays they produce, which there was no way for Carrington to measure, right? So
Mm-hmm.
we don't really know how it would stack up against modern measurements of flares. All we can do is sort of extrapolate from his observations. So his observations were very good, right? He did the best he could at the time,
Mm.
and so there's detailed notes, and there have been papers trying to reconstruct from his notes, what we think might have happened. And those reconstructions say, yes, this flare was huge. It's probably the biggest flare that we've ever recorded. Um, and so the associated CME that caused the geomagnetic field to change a day later was probably also one of the biggest ever recorded. But there were no spacecraft to make measurements of it, so we don't know.
Mm-hmm. Mm-hmm.
There were measurements of the magnetic field of the Earth, so we do know the geomagnetic storm caused by that event was huge, one of the biggest ever recorded. But again, if you want to look back beyond the record of magnetic fields made, so the magnetic field of the Earth has been measured for about 200 years now.
Okay.
So we've got about 200 years of data. But if you want to go back beyond that and say, was this Carrington event, a once in a million years event, or a once in 100 years event, and we've just been lucky and haven't seen one for 200 years? That's really hard. So what people do is they measure radioactive isotopes in tree rings and ice cores, because when you have the radiation from the solar flares hits the Earth, it makes different isotopes of different atoms in the atmosphere that eventually come down to the ground and gets locked in the trees and the ice.
Oh, wow.
So,
Okay.
so yeah, so there are people that study ice cores from Antarctica, and they measure the isotopes of beryllium and stuff that are other chemicals that are in the ice cores, um, and they try and estimate the space weather based on that. And
That's
yeah,
amazing.
I know it's wild. And in that sense, the Carrington event isn't that uncommon, right? Like
Mm-hmm.
they would say they were bigger events, like over the last 20,000 years. It's one of the bigger events, but it's not the biggest. So, but that's we're extrapolating a lot from a very small data set, if you see what I mean, that
Mm-hmm.
has a
Mm-hmm.
lot of effects in it that we don't understand. So
Mm-hmm.
it's really really hard to tell from that whether that's true or not.
Mm-hmm.
And so the Carrington event is what we call the reasonable worst case scenario, because we've seen it happen. We have an estimate of what its effects were, um, and we know that, you know, at minimum, it's a 1 in 200 year event, if you see what I mean, because it happened
Mm-hmm.
once. So the problem with statistics, or with data like this when you do statistics, is if you see something once, you actually don't know how common it is. You need to see something 3 or 4 times before you can actually really estimate its probability properly.
Yeah, time between
So
them.
yeah, so we don't really know. We know it's possible, but
So, but no one then, no one, you know, normal, like not studying it, noticed, right? Whereas now, if something like that happened,
yeah. So the general
like,
population. So there were some things that were noticed. So the aurora was visible all over the world. So there are paintings of the aurora, where you can see like a Caribbean island and a ship, and then the aurora.
oh
And
my gosh.
that's really real, right? You wouldn't have seen that for 50 years or something. Like no one currently living in the Caribbean has probably ever seen the aurora at
Yeah,
home.
yeah.
But on that, for a couple of days around that event, that did happen. Um, and
I can't imagine the theories, you know,
mm,
for what they
I
figured was going
imagine.
on.
So there's lots of newspaper reports about it, right? You can read the newspapers from 1859, and they're like, oh, there was a beautiful light in the sky, and everyone was very happy to see it, and a little confused. And there actually are some newspaper articles that say, you know, this is an effect from space. Like the reporters in 1859, not all of them, but some of them, managed to go and find a scientist and get the information from them and interpret it as correctly as they could at the time. So it was pretty
Right.
amazing. Um, the other thing that happened is, they just laid big transatlantic telegraph cables, so
Mm-hmm.
you could send a telegraph from the UK to America. And the way they worked was, and they had a big battery, and then the operator had that little metal thing, right, that you go do 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 with to send the telegraph in Morse code. And so what happened was they found that they could disconnect the batteries and still send telegraphs because there was just enough current flowing through the wire from the geomagnetic storm. They didn't need a power supply. Also,
Oh, it's like the whole Earth, the whole planet's like vibrating with energy.
yeah, well, there's a big current, a big electrical current that's flowing all the way around the Earth, and normally it would just go through the oceans and the crust. But if you lay nice copper cables down, then that's the most conductive thing, and so the electricity flows through that. So we spent the last 100 years covering the world in beautiful conductors that that current would like to flow through. But and the grid is designed to handle stray currents like that. But the question is, if it's a 1 in 1,000 year or 1 in 200 year event, have you designed it for that? And the answer is probably not. But what's the worst that could happen? Well, there'll be a blackout for a while. So the thing that's really okay, now we're getting into like the fringe territory again. But what happened with the dam in Quebec is an interesting example, because we also, in this country, we have nuclear power plants, right? And just like a hydroelectric dam, you can't turn them off, at least not rapidly. So if we have a
it's a matter of opinion.
So if you have a situation like happened in Quebec, then there are safety issues around nuclear power. And what do you do with the power station when you disconnect it from the grid? There are ways to handle that. I'm not saying there's going to be a nuclear explosion, but it's not quite as simple. Like with a gas power station, turn the gas off, no problem. With a nuclear power station, you can't do that, right? It's on. So just the management of that is a bit more tricky, and so it is worth being prepared for this.
Yeah. And there are parts of the world where nuclear power stations are not that far away from where people live, right?
Absolutely, yeah. I mean, France is almost entirely powered by nuclear power, so there's lots of nuclear power stations there. And we've seen with the Fukushima disaster in Japan, right after the tsunami, that nuclear disasters are not something that is impossible, right? Chernobyl, Fukushima, all these things have happened, and we should just bear that in mind and be prepared.
And you said earlier about like it affecting satellites on a sort of wider scale. Is it because they are further out, or is it just because of how many there are sort of covering?
So for satellites, it's not the electric current that's the problem, it's radiation. So we haven't really spoken about radiation, but solar flares are these intense bursts of energy, and so we classify them based on X-rays, which is a kind of radiation, but they also produce other radiation as well. And the coronal mass ejections that travel out very rapidly from the sun also create radiation. So they're traveling so fast, they're traveling millions of kilometers an hour, and they're traveling so fast that they pick up the gas that's in front of them, and it sort of reflects off them as they're moving out, and then shoots off very fast, and so it becomes radiation.
Well, okay, right.
So solar flares and coronal mass ejections make a lot of radiation. Geomagnetic storms, the current that's flowing in space that causes the current on the ground, that's also made up of particles in space, and so some of those get accelerated to very high speed as well and become radiation.
Right.
And our satellites are sitting out there in space, and so they're affected by all of these three kinds of radiation, sometimes simultaneously. So there are radiation monitors on satellites, and the range of radiation that you get is staggering, right? The background radiation is here, then the peak radiation you can get in a space weather event is 1 million times more than the background. So you can't just say, oh, it's okay, we'll manage it. You have to prepare for it, because it's so much more intense that it starts weakening the actual material that the satellites is made of, right? So the computer chips are semiconductors, so they're made up of insulators and metals, and the radiation comes in and it charges up the insulators, and then you get sparks effectively that move through the inside of the satellites and just melt the electronics.
Whoa.
So
because I always picture what radiation does to living life, right? And it just kind of like it destroys it, right? Melts it. Cells are going crazy all over the place.
Yes.
What happens
exactly
to
the same thing happens.
Right.
Sorry, go ahead.
No,
exactly the same thing happens in the satellite, right? So the satellite doesn't have DNA. So for like you or me, if we were exposed to that very intense level of radiation, it would be very bad for us, and we would get radiation sickness and maybe die. Um, the reason that happens, as I said, is because the radiation hits your cells and it breaks apart the molecules inside your body in your cells, and the cells die. Or if it doesn't kill you, you might get cancer because it mutates the cells and they replicate in a bad way, and then you've got cancer, right? So I mean, satellites can't get cancer, but the same thing happens to them, even though they're not made of cells. They're made of metals and plastics and things. But the same thing happens, right? The radiation comes in, it hits the atoms inside those materials, and it moves them. And that's bad. That's just bad for any material. So if you put plastic in space and it's exposed to radiation, it becomes really brittle and starts breaking. And if you put metals in space, and then if you put two pieces of metal like this with a gap between them, they will charge up differently because of the radiation, and then you'll get a spark that goes between the bits of metal. So satellite design is a really interesting bit of engineering, because you don't just have to consider making sure it doesn't fall apart when it's launched and how it's going to work. You also have to consider, well, I can't allow there to be big differences in the materials it's made of that might make electric currents flow because of the radiation. So it's a very tough engineering challenge to build a satellite, actually.
But there are lots of satellites up there now, right? It's quite a busy
there's several
space.
thousand satellites, several thousand active big satellites, and many, many millions of little bits of junk, right, floating around. So the several thousand active satellites all sit there, and they get hit by this radiation more or less the same. If you think that they are the ones in geostationary orbit, for example, are 6 Earth radii away from the Earth. So Earth is, to them, looks like this kind of ball in the sky, like that, and the sun is over there somewhere. So if you're in geostationary, pretty much all of the satellites get hit by the same radiation, roughly, over a day.
Right.
So, and those are the satellites that we do telecommunications with, right? So if we did have a really, really massive Carrington style event and the radiation was incredibly intense, then you could potentially damage or disable or destroy a very big fraction of those satellites, because they're all exposed to it at the same time.
Yeah.
So here on the ground, the atmosphere protects us from this radiation, right? There's a very thick atmosphere between us and space that most of this radiation gets absorbed by.
Right.
So we do see radiation from the sun on the ground, but very rarely. They're called ground level events, and there have been 72 of them since about 1900.
Okay.
So
they're okay
because,
then.
Well, they are part of our background radiation that is part of that whole background radiation that we just live with. But they are measurable. They're just rare. So there's been
Is there any point, like, out with the satellites that it's gonna? How are we fitting so many out there? Are they just gonna have to start going further and further out?
So I mean, space is huge, right? If you think about the whole surface area of the Earth and you put 1,000 things on it, they'd be very far apart. Then you're going to multiply that by the fact that it's 6 times further away. So you've got this ring of satellites that. So there is kind of congestion in space, but it's to do with the fact that the satellites in geostationary want to be above specific locations, and that's where people live, right? So if you're in Europe, you all want to put your geostationary satellite above the equator, above Africa, because that's how you see it from Europe. So there are particular spots in geostationary that are, and that's just related to where people live. So above America, above Europe, and other places that have high populations that are profitable to put a satellite there. That's where you put the satellites.
But it's not a great concern right now of it being like too much going on, or satellites crashing together or anything like that.
That's a great question. So there is something called the Kessler effect, which is named after a NASA engineer called Don Kessler, who predicted this in the 60s or 70s. And so he said, back then in the 60s or 70s, they were launching, maybe 100 satellites or something. But he said, if we keep launching them like this and we let junk fall off our rockets, and sometimes our rockets explode, then there will come a point where the junk starts hitting other junk and making more junk. And once that happens, you have a cascade that continues. And that's the film Gravity, right? With Sandra Bullock and is it George
Right.
Clooney? Anyway, but that film is basically the Kessler effect in action of space junk hitting other space junk,
It's
making a
like the
cascade.
great garbage patch in the ocean.
Exactly, and
Right,
so
okay.
so there is a risk of that happening. At the moment, the forecast for space junk is maybe somewhere in like the 2040s or 2050s we would get to the Kessler effect. But there's been a big
Okay.
international effort to reduce space junk. So there's no binding laws, or there's very, very few binding laws in space. So it's really like the
No
um,
man's land.
yeah,
The
the
new
deep
no
ocean or
man's
whatever.
land.
Yeah, yeah. Um, but one of the few international agreements there are that it's not binding, but everyone's trying to do it, is to reduce space junk. So what that means is when you launch something, apart from the satellite that stays in space, everything else has to fall back down and burn up in the atmosphere. And then
Okay.
when your satellite is done, it has to either come into the atmosphere and burn up or move away into some graveyard orbit that no one wants to use for anything else. And more or less, people are trying to do that. So space junk, it's not decreasing at the moment, but it's also not massively increasing. So,
Is
as
that
long as we stick to those, as long as we stick to that, it should be okay. But
it's
it
kind of
is
like
it is a risk.
landfilling something or incinerating it. But
Yeah.
is that quite speaking as someone who's always
Mm.
thinking about environmental destruction, is that bad for our top level layer?
Um,
Um,
I
is
mean,
it
the
kind
top
of
of the
like a
atmosphere. Yeah,
yeah?
it's a good question. The top of the atmosphere is hit by meteorites every day, all the time. So
Okay.
you can actually see if you have a radar, you can see the meteorites burning up in the atmosphere all the time. They're like shooting stars, right? Just little bits of dust, tiny little bits that go through the upper atmosphere. So that happens. There's millions of those every day, and the upper atmosphere actually has measurable quantities of metal in it just from these asteroids, meteorites, I should say. So our space junk does add to that, but it's not. I don't think it's going to cause a major problem. We'd have to put a lot more stuff in space before it was
I feel like
really a
maybe
big
we're at the
deal.
time now, at the beginning of the Industrial Revolution where they
Mm.
started using fossil fuels and, well, it's just a tiny bit and stuff happens all the time. And then,
That's the thing.
in a couple hundred years, it'll be like, oh God, why didn't we recycle or something?
Yeah, no, I mean that's a good point, and you know, the way space is being used for satellites is very, very different now than it was 20 years ago. You've got to think about SpaceX putting constellations of thousands of satellites into orbit. That's There are something like about 2,000 operational satellites at the moment, but Elon Musk wants to launch 30,000 more. So it's not like a
Right.
small increase. He is putting 15 times the total number of satellites. That's what he's
Wow.
put in a patent for anyway, right?
Right.
May or may not. He himself has said, "Oh, I'm not actually going to do that. That's just to like test the water and show what's possible." But but
Right.
but who knows? He definitely has plans to launch hundreds, right? So
Yeah.
so it's the space
Well,
junk thing for that is a real problem because if you fill up the low Earth orbit, just above the atmosphere with all these satellites, even if they're carefully managed and they don't break apart, there's still this massively increased risk of that happening. So it's yeah,
how
we're
do
definitely in
you
that Wild West period of like you said, we're just building satellites like we were just building cars, and at some point we might decide this is a terrible idea and it will be too late to do something about it. But um,
don't
yeah.
say too late. Don't say too
Well, so I
late.
mean, the good news is if it's especially if it's low Earth orbit, so below 500 or 600 kilometers altitude, things don't stay there for very long, right? There is atmospheric drag that brings them down, and over a period of time, they will burn up. So, geostationary is a different problem. Once you're in geostationary, you're there forever, unless you move yourself. So, that's a different problem. But in low Earth orbit, at least, even if there is a disaster of space junk, it would fix itself over time. Um, Not a very short time, right? It'd probably take 50 years, but it would, on the scale of human life, it might be disappointing, but the next generation would be able to do satellites. So,
Yeah,
yeah.
yeah, that can fix it. How do you sort of feel about Elon Musk and the sort of growing private companies in the space industry? More attention is sometimes paid to SpaceX than to NASA now, right?
Yeah, it's interesting. I have mixed feelings. So I think it's great that industry can take over some of the things that the national space agencies were doing because it frees up that money or that capacity in the space agency to do other things. And it is right to try and turn these things into businesses, because that gives them some sustainability, and it means that we're not just doing this for fun, if you see what I mean. Intellectual investigation is great, but at some point you can say, we've done enough of that, let's move on to something else. Whereas if it is a ongoing business that is profitable, then it will continue, and there's some reason to do it, into the future. So I do think space as a business is a good thing, and I think Elon Musk is a very inspiring kind of character who has big ambitions and big ideas, and that's
and makes
what's
them
needed.
happen. It's mad.
Yeah, which is very impressive.
Yeah.
On the other hand, he's also, he's a bit of a caricature and a cartoonish figure sometimes, and he is the kind of person who does stuff and then asks permission, rather than making sure it was the right thing to do to begin with. So many innovators are like that, because you need to have that drive and ambition to get things done. On the other hand, it's not very fair or equal. So if we're thinking about if he does put 10,000 satellites in low Earth orbit, for example, no one else can use those orbits because he's already got them. It's just a bit like squatting, right? You say, I've got my satellite there, so you can't have it. So there is a kind of like a web domain squatting, right? I register the domain name of thousands and thousands of domain names for like 10p each. And then some business comes along and wants that name. Well, now I'm going to charge them thousands of pounds for it. You can do the same thing in space by saying, I'm going to launch loads of cheap satellites into all these orbits, and they're mine now. If you want to use this orbit, you're going to have to pay me, or so.
Right. So it is kind of like a little move from socialism almost to capitalizing on space.
Yeah, definitely. So until 10 or 20 years ago, space was a national playground, right? You had to be a nation with the space agency to be there, and so I wouldn't say it was socialist, but it was the use of it was defined by what the nations wanted rather than what individuals wanted.
Yep.
Whereas now, it's moving more towards individualism, in the sense of individual companies with very specific desires for customers can do that. So
I feel okay about Elon Musk. I think just because of his work with Solar City and Tesla, I feel like he's a smart guy. He's looking at problems as a whole, and he knows that sustainability is important, and the running of certain things that we have put in place is is bad overall in the long run. But I do worry, as you were saying, that he will he will carve a path out, and he will change things and change the landscape, and then some more people will come along, and it will be open for play then for whoever.
I think that's right, but I mean, I'll give you an example. So there's because there's so little regulation in space, right? There's the Outer Space Treaty at the UN, and that's about it. And all that really says is, don't touch my stuff, right? If it's my satellite, you're not allowed to touch it. And we're supposed to help each other. It's a bit like the rules of deep sea. Like, if a boat is in distress, you go and help them, no matter who you are. It's the same in space. Like, if my satellite has a problem, you're supposed to help me. That's all it says. That's the rules. There's nothing else.
Wow.
And so the problem is, because there's no international regulation coordination, you get things like the international astronomy community is spending nearly $1 trillion. Is that right? No, sorry, I'm massively focusing. $1 billion on something called the Square Kilometre Array, SKA, which is this massive radio telescope. It's going to make the best pictures of the distant universe in radio ever made. They want to look at the Big Bang and look at dark matter and look at black holes and galaxies and all this massively cool science. But it's a radio telescope. So if you fill the sky with thousands of satellites that emit radio, it's a massive problem.
Right.
They've purposely built SKA in South Africa and Australia in the middle of big deserts where there are no people, to keep it away from mobile phones. And when a plane flies overhead, that's a real problem for them. It's like they try to put it away from the common air traffic routes.
Right.
So astronomy, ground-based astronomy, has a real problem with SpaceX filling the sky with thousands of satellites, because until now you could look at patches of sky away from satellites, or if a satellite went across your field of view, it was just like one little trail over there, and hopefully it wasn't near the thing you were looking at.
Mm.
But when you see the SpaceX satellites go through the field of view, it's like a massive fleet of satellites kind of across your field of view, making a whole load of stripes.
Right.
And so, I'm not that kind of astronomer, and there are ways you can deal with that. It's not the end of the world, but there's massive international collaborations that are trying to benefit the world and do
Mm-hmm.
science.
Mm-hmm.
That if it had been a government project, there would be a way for those scientists to go to the government. Like in the UK, SKA headquarters is in the UK. They lobby the government, and they would say, no, you can't launch all those satellites, you'll ruin our experiment. And the UK
Mm-hmm.
government
Mm-hmm.
may or may not listen, but at least there's a mechanism. Whereas there is no mechanism to stop SpaceX from launching those satellites, right? He is a private individual with his own rocket and his own satellites, and he is licensed by the US government to launch them. So that's it. Like,
Mm.
other than putting sanctions on the US government or refusing to buy SpaceX products, there's nothing we can do as scientists to stop that.
Who has he applied to for the patent for all of these satellites?
It's
The US government.
Yeah, it's all internal to the US, right? So
Right.
so even though the sky is an international thing, right? If I launch something in space, it will fly over your country. It just has
Yeah.
to by physics. So even though it's this international thing, it's regulated. Each nation regulates their own launching. So, the U.S. government has been very clear on this. The U.S. government wants a big boost in the space industry, and so they're just saying yes to stuff, right? They want
Mm-hmm.
their industry um, to to lead in space and make money out of space, and so they're just allowing it to do whatever it wants. Um, and that's what I mean by I'm conflicted. I think what is happening is great, mostly,
Mm.
but there are some things that are not great, and there's no way for the common person to interact with that to stop it.
Mm-hmm.
So, like, we really are in this Wild West thing. It is like the cowboys come into town and rob the
Mm-hmm.
bank. The question is, are we going to accept that for now, because in the end we'll have a massive new resource, or do we want to regulate that now and try and be fairer as we're moving on now?
Yeah. I feel like it's almost inevitable that we will end up, yeah, creating this newer space age where there's a lot more activity in space, and everybody on Earth has, I mean, we already do, but despite having mobile phones, but that it's a lot more present in our life. And
I,
yeah,
I agree.
we're at the start of it now, where we're trying to say, okay, how do we make this fairest and best for everybody, right?
Yeah, and no, I completely agree, and I think space is a massive frontier that we are expanding into, and what we need are well qualified people who know electronic engineering, mechanical engineering,
Mm,
aerodynamics, um,
mm,
data transmission. So we need a lot more people who know about radio and lasers and how to transmit data.
mm.
Um, it's a massively exciting time, and there's a lot of opportunities out there. You don't have to be Elon Musk to make it in the space race, right? There's
Mm, mhm.
there's companies in the UK that are doing just fine. Surrey Satellites is amazing. Um, Clyde Space is this CubeSat company, right? They build little tiny satellites this big called CubeSats. They were just bought by a big international company. Um,
What does a little
so
satellite like that serve?
they're mostly for technology demonstration, for learning, so students can build them
Oh,
and launch them.
cool.
So, I mean, we actually built one at UCL where I used to work. They're 20 centimeters long, so literally this long, 10 centimeters tall. So they're this big. You can pick them up and hold them. And they've got solar panels on, a radio at one end, and some kind of experimental sensor or thing on the other end. So what they're used for is to test things. So
Mm,
we when we launched our satellite, we put a sensor on it to try and measure the composition of the upper atmosphere.
mm,
Um, Other people put on radiation detectors or cameras. So there's a company called Planet Labs, which has hundreds of these CubeSats in orbit with just effectively fancy shop bought cameras, right? Like the DSLR camera that you'd buy to if you're enthusiastic about photography, to go and photograph things. They've got
Mm.
that in a satellite. They've got hundreds of them looking downwards. And their objective is to take a photograph of everywhere on the Earth every day.
Wow.
And they're doing
Cool.
that, and they sell it. So you can buy the Planet Labs product, and it will help you monitor disasters with
Right.
farming,
Mm-hmm.
all kinds of different stuff. So
Yeah.
I think they're partnered with Google now, or one of the big tech companies anyway in Silicon Valley. They've been bought by, and um, so my point is, you don't have to be a billionaire and own a massive company to do space.
Mm.
There's Teesside University is launching its own rockets. There's Egglescliffe School in Yorkshire is building a satellite and going to launch it with a company in just outside Newcastle.
Uh-huh.
So if you're a teenager at school and you want to do space things, you find it cool, go out there and look. There are things you can do. The
There's stuff happening.
the Ambasat kit, it's 140 quid to buy a little electronics kit that you do yourself at home. You can do some soldering and you do some programming and put it together, and you post it off to Ambasat, and they'll launch it into space for you and send you the data. So
Where do they launch it to? This is part of everything
Mhm.
that's out there that we were talking
it's
about.
effective. I mean, not to be mean, having just said it was great. It's effectively space junk, right? They launch it into
Yeah.
low Earth orbit, about 400 kilometers up. Um, they they chuck them out the side of their satellite, and they just kind of drift off for a while, and they last for 6 months, and then they enter the
Right.
atmosphere and burn up.
Right.
So
Right.
it's introductory space technology for secondary school students and university students at a price
Get
that's
people
affordable.
excited. Yeah.
Um, but it
Yeah.
doesn't last forever, right? It's just a few months of
Yeah.
stuff. But that's how you get that's what we need to get that future generation of people to work in these companies to expand into space, right?
Yeah.
We're never going to get there unless we've got thousands and thousands of people who know what they're doing, working
Mm.
hard, and that means we need people to be interested in space and want to do the electronics of satellites and the mechanical design of satellites and
Mm.
building rockets and launching rockets. And there's operations teams, right? People don't think about this, but Solar Orbiter, we were talking about at the beginning,
Yeah.
there's a whole operations team in Germany and in Spain that operate Solar Orbiter, and that's hundreds of people altogether that have to know how everything works and make little binary commands and send it from a big radio dish out into deep space and
Yeah.
all this kind of
Yeah.
stuff. So
Yeah.
there's all kinds. You
It's a
don't have
big
to be
industry.
you don't have to
Yeah.
be into electronics, right? There's lots of different things that you could be interested in and have a career in space. So
Yeah. I mean, yeah, it sounds like the future of study of space is as well. There's so many areas other than the missions that you currently have going on Solar Orbiter that we talked about. What if you had unlimited funding now and unlimited people to help you? What sort of one question would you
gosh.
ask? And it can't be aliens or anything like that. Let's
Mhm.
stick to space weather. About space weather,
That's a
what would you
very
want to
difficult
know?
question. Gosh, I mean, I think we're very, very lucky at the moment in that we have recent missions that are very that focus on space weather and that are very interesting. So NASA launched Parker Solar Probe, which is to go very, very close to the sun, and ESA
Mm,
launched the Solar Orbiter. So we're actually very well covered right now. I think um, if it's space weather-ish, but a scientific investigation, and I'm allowed anything,
yeah,
then I would
absolutely.
go the opposite direction. I would say I want to go to the edge of the solar system, right? The the only spacecraft that have left the solar system are Voyager 1 and 2. And oh well, there's perhaps New Horizons and a few other ones that are getting there, but they're the only ones that have made observations of the edge, like where does space weather end, right?
Right. How far does the sun
Hmm.
impact reach?
Exactly. So there's a big international project that's being studied in America called Interstellar Probe, with the
Hmm.
idea of actually shooting towards the sun very fast, doing a gravitational slingshot very, very close to the sun to get up massive speed and then just leave the solar system. And that excites me probably more than any future planned mission at the moment. It's
Hmm.
not funded. It's not necessarily going to happen. But if you gave me unlimited money and people,
You'd make it
that's what I
happen.
that's what I'd do, because you're going to get closer to the sun than Parker Solar Probe and find out some things about the sun.
Uh-huh.
and then for the rest of my lifetime, it's going to be traveling away from the Earth, discovering new things in deep space that have never been seen before.
Whoa.
And I think to understand how our star interacts with the gas clouds around us in our galaxy, and to eventually maybe measure the winds that have come off other stars and see what they're made of, you know,
Right.
is that gas cloud outside of the sun made of the same stuff that the sun's made of, or does it have organic? You asked me not to talk about aliens, but uh, are these gas clouds rich in organic molecules, and
Mm,
or is it just sterile dust?
mm,
That's a really
mm.
massive question that you can look at it with a telescope, but going there and actually measuring it in space is important too, right? So
So we
um,
don't like our solar system doesn't exist as a sort of island in space. It's possible that we're interacting with other stars and other solar systems nearby.
yeah, so I mean, our solar system, the solar wind blows out from the sun, and somewhere out around the orbit of Pluto or a bit further out, it stops, right?
Mm,
The solar wind slows down, and it pushes up against gas and dust that exists outside of the sun.
mm-hmm,
So that's called the local cloud. So the sun is
mm-hmm.
moving through this cloud of dust. Um, we don't, we've measured it with telescopes, but we've never sampled it. We don't really know, we haven't investigated it that much detail. Um,
Mm-hmm.
and then there are other stars nearby, right? Our closest star is like 4 light years away or whatever, and it has its own wind and its own bubble. Well, I won't say never. In my lifetime, I don't think we're going to go there and measure that star, right?
Uh-huh.
But we could learn something about the stuff that's between the stars, and that would help us model the environment around the other stars as well. So
Right.
that's
And
a really exciting science question that's got,
yeah.
it links to space weather in the sense that, know, whether the sun is more or less active expands and shrinks this bubble around the sun.
Yeah.
Um, that excludes more or less of the surrounding gas. So
Right. Yeah. And we theorize that most stars sort of play like do the same thing in terms of coronal mass ejections and stuff, or different types of stars and different sizes of stars, very, very different.
so that's a big and difficult question actually. So
Yeah.
the we certainly know that other stars have winds because you can see through telescopes. Some stars seem to have like a bow wave around them. So you can see the star is here, and then there's like a bow wave where the star is moving through the gas around it. So something must be coming out of it to push that gas out of the way and make the wave. So we think it's very common for stars to have some kind of wind leaving them, right? Just the balance of pressure between the star and space means that there must be winds leaving stars. Whether they have space weather in terms of flares and sunspots and CMEs,
Hmm.
that depends on whether the star has a strong magnetic field and a magnetic dynamo that flips the magnetic field around like our sun does.
Hmm.
So we have measured flares on other stars. We have measured or star spots, I should say, on other stars.
Right.
We can't see them. We can't resolve them with a telescope, but we can see the stars brightening and dimming, and so there's definitely evidence for that. But how widespread it is, whether there's a common mechanism, whether what we see on the sun is typical or not, we don't really know. Um,
Wow.
that's a different mission. that so
Yeah.
there
Yeah.
um,
That's the
that
second project.
Yeah, I mean, there are plans for a UV telescope in space that doesn't look at the sun but looks out at all the other stars. The reason to have it in UV is that solar flares and space weather are mostly recorded in X-rays and UV light. So you want it to be in that part of the spectrum rather than visible light because you'll see more of that activity.
Hmm.
So that has been proposed to the European Space Agency in the last couple of years. So it's under review. That ESA is currently doing a big review of what mission should we do for the next 20 years. It's called Voyage 2050 because it's for the 2050 is like the end point of that cycle.
Yeah. Yeah.
So who knows? In the next 5 to 10 years, we'll find out what missions will be launched between now and 2050, and one of those might be a star spot, like star weather mission.
Yeah.
Um,
Well, some
one
of
of
your
those.
students might be running them
Yeah,
in 20
absolutely.
years.
I really hope so. Yeah,
I think
absolutely.
so.
I mean, I will also be doing my best to make sure that these missions kind of come about as well, right? I mean,
Yeah.
I can't influence the European Space Agency that much, but you know, whenever there's an opportunity to, we put in our input and our ideas and say, you know, you really should do this. It'll be great. So
Yeah, yeah.
I'm
Well, it'd just be
around there.
fascinating to know how special is our sun. I mean, we know our planet is special for having the shield that allows us to exist, right? And how special is our sort of solar system, our sun.
Yeah.
So funny that you're like blocking the sun out right now as we're
No,
like talking about it.
this is the working from home problem, right? I mean,
Yeah,
we
yeah.
shouldn't complain, but it is a
No.
bit difficult sometimes.
Yeah, there are ups and downs, but thank you so much for sharing all of that. That was
You're very
yeah,
welcome.
I found that very interesting. So
Oh, I'm glad.
yeah, yeah, that was
Yeah, I mean,
awesome.
anything you want to talk about in the future, let me know.
Yeah, I'll come back in a few years and say, you know, how have you, you know, did you propose this thing and how have things gotten through? And maybe when Solar Orbiter is
Yeah, in a year's time or something.
some,
So the first data release from
yeah.
Solar Orbiter just happened, but we won't get the really exciting photos for another year or so, just
Oh,
because
wow.
it's going to take that long for the orbit to reach the right place to take the photos. So
Mm-hmm.
yeah, in a year or two, we could have another conversation about
Yeah,
you know, what do we learn from the first couple of orbits of Solar Orbiter, and
yeah.
hopefully there'll be some really exciting videos and pictures to show of the sun in close up.
Oh, I'd
So
love that. Yeah, we can have a catch up. Maybe I'll know a little bit more by then. We can, yeah,
sure.
that'd be awesome. Cool. All right. Well,
Well, good
thank
luck with
you.
everything, and
See you
yeah,
later.
see you later. Bye.
Bye.